All right, hi everyone. So it's a real pleasure to introduce Tree Dow. Tree's just done, I think a lot of spectacular work at the intersection of ML and systems, things to do with attention, long context models, and I'll just let Tree take over. All right. Raise your hands if you have questions during the talk.
Yeah. All right. Hi, everybody. Really excited to be here. Thanks for the invitation. So this talk is going to be at the intersection of machine learning and systems, as Shyam mentioned. And basically, there's been a ton of really exciting progress, especially recently. So I just want to share some of these progress with you guys. And the talk is relatively informal, so feel free to stop me and ask questions. OK, so we'll get started. So in this talk, I'll talk about how you design models for modern hardware. So the motivation, and we've seen this in the last 5 years or so, is that progress in AI has been driven by scaling laws. So these are empirical laws that show as you increase the amount of compute, as you add more compute, as you have better algorithms, and you have more data, generally you get better models. Not only better models on existing tasks, but also models with new capabilities. So nowadays we have models that can understand humor, can write jokes, can transform images into glibby cartoons, and so on. So just 5 years ago, these things were sort of unthinkable. But now we have actual systems that you can pay, I don't know, $20 a month to use. So where do we go from here, right? And for the vast history of AI, for the vast history of our 70 years of our discipline, we were mostly concerned with do things work at all, right? And now things are working. So as we move some of this from research labs to products and delivering this kind of intelligence to a lot of people, the question now is, can we deliver that kind of intelligence in a cost-effective manner? So now we want to focus on intelligence per dollar. And intelligence per dollar, you can factor that out into intelligence per flop. A flops is a floating point operation, multiplied by flops per dollar, right? And in this talk, we'll focus on actually both parts, but I'm trying to motivate why you need to care about both. So intelligence per flops, I would call this algorithmic or data efficiency, which is given a fixed amount of compute, a fixed amount of floating point operations. How can you train a better and better model? So that usually comes down to having better data, having better algorithms, and so on. And the other side of the equation is flops per dollar, which is given a fixed amount of money. How can you get as much compute as possible, right? And that's a question on the hardware side. And there's been amazing progress there as well. We're seeing 2 to 3x improvement in flops per dollar every 2 or 3 years, which is way faster than Moore's law, right? And so I would argue that there's this really fertile area to work on, which is this intersection of algorithms and hardware. So you're tackling both sides of this equation. And so for this talk, I'll illustrate with some examples, some of the things you can do at the intersection of hardware and algorithms. So the main idea I'll talk about is you can design hardware-aware algorithms. So algorithms that take advantage of the hardware that they run on. And in particular, I'll just focus on one example of state space models, where turns out you can exploit the memory hierarchy on the hardware to design a much more efficient sort of state space model or recurrent models that can do actually quite well at sequence modeling, can rival transformer architecture, and so on. And this started as joint work with Albert Gu, who's now a professor at CMU. OK, so the talk's going to have 2 parts. The first part, we'll talk about state space model, RNNs, linear attention, and so on. We'll look at some of the ingredients that you need to have a really strong architecture. and to have really high hardware efficiency. And in the second half of the talk, I'll talk about how to design things like attention variants that take advantage of hardware, really focusing on inference. And then both the state space and the attention is going to come together with hybrid models. We're going to show that they can be a lot better at inference. They can be a lot better at task time compute. OK, so let's get started on the state space. So nowadays, most of the sequence, most of the applications in modern deep learning are now powered by these deep sequence models, from text to image to audio to video. And they all share pretty much a common sort of architecture as backbone. And typically, this is a transformer. And as we want to understand sort of the trade-off between different architecture, one really useful way to look at these different architectures is through the lens of the autoregressive state. So I'll explain what that means. So the autoregressive state is just whatever the model needs to remember from the past to predict the future. And we'll see that this is a really useful lens to look at different architectures. So for example, you can look at recurrent neural networks, which were pretty common around 2012, 2016. They were state of the art for a while in machine translation and so on. And Google was deploying them for on-device translation. So the way they work is that you have different time steps indexed by t. And you have, at each time step, you have a fixed size hidden state h of t. And h of t is going to be a function of the previous hidden state, h of t minus 1, and the current input, x of t, right? And then you can design some update function or some transition function, f of theta. And f of theta is some parameter that you're going to learn. So typical examples include the LSTM or GRU. So these are different instantiation of the same idea that you can have a fixed hidden state. And this h of t essentially contains all of the information you need from the past in order to predict the future. And now state space models, in some sense, you can view as a simplified version or a linear version of these RNNs. So they actually look quite simple. And their history go back to the 1960s. So if you heard of Kalman filter, that's sort of where state space got started. So again, we're still going to have these hidden state h of t. We're going to have the input x of t. And we're going to have output y of t. And they're all linearly dependent on each other. So the hidden state h of t is now a linear function, at times h of t minus 1 plus bt times x of t. So you force a linear form on the recurrent update. And then the output is also a linear function of the hidden state h of t. So the only twist going from RNN to state space is that you do this dimension blow up, where you treat the input as a bunch of one-dimensional signal. And then the hidden state is going to be n times larger than that. And we'll see why this is important. So we're going to turn the 1D input, x of t, into an ND hidden state, h of t. And n is, you can think of in the order of 10 to 100, right? And then you're going to do a projection down to 1D to get the output, y of t. So conceptually, it's very similar to RNNs. It's just the hidden states, the hidden state update is linear, and the hidden state is usually quite a lot larger than the input. And so when we look at the autoregressive state, we see that these things have a fixed size state vector, right? That means the model is forced to do very strong compression. It has to compress whatever it has seen in the past into a fixed size vector, right? And because of this, you can immediately deduce the pros and cons of these models. So on one hand, this is efficient during training and inference, because to do inference, you don't need to look at the entire past. You only need to look at the the hidden state that has compressed all that history and then used to predict the next time step. So it's going to be constant time when you want to predict the next token. And during training, you can work this out. It's also going to be linear time during training. But these things don't do very well on information-dense modalities, simply because for language, usually there might be a lot of information that you need to compress, and that might overwhelm sort of the size of the state of these RNNs and state space models. Now, on the other hand, we have the fantastic attention. Actually was invented in, I think, 2014, 2013, something like that, but got popular with the transform architecture in 2017. And there, the inductive bias is no longer, we want to compress the history. The inductive bias is we're not going to compress at all. We're going to sort of store the entire history. So this is known as the KV cache. And the way it works is every time you want to predict a new token, you sort of compare the current token with the entire, with all the tokens that have come before it to see which one is similar, and you take sort of weighted combination of the previous tokens. So just by looking at the autoregressive states, we see that there is this all-to-all connection between all the tokens. So generally, these models have very strong performance, and they can model long-range dependencies quite well. But the flip side of that is that during inference, if you want to predict the next token, it's going to be linear time, linear in sequence length, because you got to look at the entire history, right? And similarly, during training, it's going to be quadratic time. So if you want to double your context length, then you're going to pay 4x the cost in terms of flops. So we want to get sort of the best of both worlds. So we still want strong performance of transformer, but we want efficiency and linear scaling of these state space models. And turns out there are a couple of ingredients that you need. One, you need a relatively large state size. You need an expressive state update, and you need efficiency. So I'll explain each of these. So number one is how large is your autoregressive state. So previous RNNs, I would argue things like LSTM and GRUs, the hidden state was the same size as the input. And that didn't allow the model to sort of store too much information from the past. But with the state expansion trick that I show with state space model, where the hidden state is 10 to 100 times larger than the input, you can store a lot more information by a factor of 10 or 100, right? And that certainly helps. I think that explains a lot of the improvement from LSTM to things like state space models or Mamba. And the second ingredient is that you want the state update to be quite expressive. So you want the model to be able to decide, yes, this is something I want to commit to memory, or no, this is not so relevant. I'm not going to commit to memory. And the simple idea how to do that is that you can make these matrices, update matrices A, B, and C to be dependent on the input. And this is conceptually a very, very simple change, but turns out to make a big difference in terms of empirical performance. For example, if you're reading a text or you're listening to an audio, right? You have some sense of like, hey, this information is really important. Or it might be filler words like that you can sort of filter out. And the way you, as a model, the way the model can do that, it can adjust, for example, the matrix B of t to control, hey, this input x of t is important. I'm going to make B of t quite big to commit more of that to memory. Or it might decide that this input x of t is not important, and you might put B of t to be close to 0. So you essentially don't commit that to memory. So that's sort of the second technique to make the state update more expressive. And the last one, as I motivated at the beginning, is very much about efficiency. Like, can you get more intelligence per dollar by getting more intelligence per flops and flops per dollar? So at the end of the day, you're going to train these models. You're going to run inference on these models. So it really matters how fast you can do this. And one of the weaknesses of older RNNs are that they were not very hardware friendly. So things like LSTM and GRUs they have sort of linear dependence between the time steps. And so when you put that on GPUs, which are very much parallel devices, they can't sort of fully use the GPUs. But if you make the update simpler, make the update to turn into a linear form, even though it sort of reduces expressiveness, it makes it easier to parallelize the computation. So turns out you can write this as an associative scan, and it's parallelizable. And previous models like linear RNNs have already exploited this fact. The other way you can exploit hardware is by sort of really thinking about the hardware when you do this state expansion. So as I mentioned, one of the tricks is to make the state about 10 to 100 times larger than the input. But on the hardware, on GPUs and other accelerators, memory usually form a hierarchy. So at the bottom here is GPU HBM, a high bandwidth memory. So this is usually quite large, on the order of 40 to 80 gigabytes, right? If you type Nvidia SMI, it shows you 80 gigabytes. That's the HBM, right? But there's some much faster but much smaller memory called SRAM, and these are usually an order of magnitude faster, but 3 orders of magnitude smaller, right? And if you're familiar with things like CPU, then you can think of it as CPU can have really large DRAM, but it can also have really fast and really small L1 and L2 cache, right? It's the same idea showing up in all of computer science. Memory hierarchy is kind of fundamental to computer science. And we can exploit this asymmetry, right? We know that we want to expand the state. We want the state to be quite large. So what happens is we can keep the state in SRAM only, right? So here I'm showing a picture of how we actually do this. Is that most of the inputs are stored in HBM, the input X, the A, B, C matrices, and so on. The output are read from HBM and written to HBM. But the states, we're only going to compute it and store it in SRAM, and we never write the states down. Turns out, writing the state is the expensive part, so we don't do it. And by not writing the states, we can make this run quite a bit faster, right? And I think this is one of the things that sort of unlock, in combination with the other two ideas, that sort of unlock a way to train linear time models at reasonable speed that can rival transformer architectures. And since then, we made some improvement. I'm not going to go into too much details. But one of the things we can do is sort of leverage the matrix multiplication units in the hardware. So it turns out you can reorder or refactor the computation and turn it into sort of these little matrix multiplications. And that's great for hardware. Modern hardware are very much a bunch of matrix multiplication engines, right? Things like tensor cores on Nvidia GPUs, on TPUs, these are called systolic arrays. In all the chips, they are very much specialized for matrix multiply. So if you can turn your algorithm into little blocks of matrix multiply, you can go a whole lot faster. Right? So those are a couple ideas, and it turns out if you train models like this, it can perform reasonably well, pretty well on average. I think on average is around the same as a transformer. But there's no free lunch, right? So we want to understand what are the trade-offs for these different architectures, and there's been excellent work from folks at Harvard, where they were looking at compression. Is it a feature or is it a bug? Right? If you want to actually compress information, yeah, it's a feature. But if you want to copy or retrieve information, it's not so great. So here's an example from this paper where they show, for example, Mamba model in this task of just looking up information from the past. I think this is called the phone book task. So Mamba model does quite a bit worse than Pythia model, which is around the same size, but is a transformer architecture. So this sort of makes sense, right? If you have a fixed state, you can't remember everything, right? And attention is clearly quite a bit better at retrieval. So there's always some trade-off, right? Like when you think about when you, let's say you want to read an article or read a paper, you would in your head have some understanding or representation of the paper after you've read it. but you're not going to remember all of the details, right? And to get all of the details, you might need to retrieve a look back at the paper. And my intuition is that attention is sort of doing that. So since then, there's been tons of development on the RNNs and linear attention side. And one of the framework to sort of derive new models is test time training. So this is excellent work from Yusun and collaborators. So the idea is you want to treat sort of the recurrent state, the hidden, the autoregressive state as a kind of fast weight. And the idea is every time you see a token, you're going to adjust that weight, and that weight is then used to predict the next token in the sequence. Right, and then you can treat it as an online optimization problem. And now, sort of the different ways you could parameterize this model turn into different model architectures, right? So depends on the loss. You can put the loss as sort of maximizing the minimizing the dissimilarity between what has been stored in the past versus the current vector, or you can minimize sort of the reconstruction loss. There are different losses you can put on it, and then you can come up with different online learning algorithms. And turns out these online learning algorithms, things like online gradient descent, and if you put weight decay and you put momentum and so on, that sort of corresponds to different RNN architecture. So this is a really neat framework from these folks. And since then, this is a sort of a way to address some of the weaknesses of having fixed size state and having to remember lots of things, right? And as a result, there's been a resurgence of recurrent and linear models, right? This RedNet from Microsoft, XOSTM, test time training, RWKV, DeltaNet, and so on. And all of these models have the same three ingredients. You want large state size, you want expressive state update, and you want efficient forward and backward pass. So one example that I really like from the folks doing test time training is they have this really sort of cute demonstration. So it turns out, so they took a pre-trained transformer, a video generation model, right? That could generate sort of 5-second videos, and then they add these test time training layers to them, and turns out they can start generating actually really coherent 1-minute long video. So we can look at some of this. So it's really cute because they took Tom and Jerry. They fine-tuned on. They took a pre-trained transformer and then fine-tuned on like 6 or 7 hours of Tom and Jerry video. And it actually works surprisingly well. There's a lot of coherence between the shot. So this is, I think, Tom in the World Trade Center. He shows up, takes the elevator. I mean, Tom and Jerry is like a very old cartoon, so I don't know back then if there was a World Trade Center at all. But he's using computers, right? Like I don't think back then there were computers. And then Jerry shows up, and I think he starts chewing on the cord. So there's actually a lot of coherence between the shots, and by using some of these layers, linear time layers, you can scale up to 1-minute video while maintaining coherence. Tom shows up to a meeting that's led by Spiky. I think his name's Spiky. Right. So these new layers, new models are actually opening up sort of new applications, things like video generation up to minute long. And I think we're, in the future we can go much longer. But for these applications, I do think you kind of need new architectures that can scale to that length, because I think a minute of video starts to get to around 128 to 500K sequence length, where a transformer can't really handle. So you need some of these new layers for this. Okay, so that's the first half of the talk. So I'll pause here to see if there are questions on this.
state space models, there's probably an overhead cost that you pay when you're moving the memory across the plane part. Is there a regime in which that doesn't make sense anymore? Like, how do you value, the cost of this movement because of the memory hierarchy versus the gains that you get?
Right. So for these, with an overhead of moving memory, when would that make sense? When would it not make sense? So I think general rule of thumb is if your sequence length is less than 1,000 or 2,000, it doesn't really pay off to use these linear time architecture. Once it is around 4,000, 8,000, then their speed is around the same. When it gets to like 16,000, 32,000, then these linear time architectures start to be faster. And this depends very much on the implementation too, right? Like on the transformer side, I'll show some of this as well. It's been extremely optimized. On the state space and RNN side, they're not as optimized. I would say there's probably a factor of 2 to 3 that you can make these things faster. I'm working on some of that. The test time training folks are working on some of that. But I think, ideally, we want to get to the point where maybe even 1K or 2K sequence length, these linear time models can be faster than. Great question. Yeah.
We think there's an architecture out there that takes the advantages of SSMs and transformers, or will this trade-off always exist?
Yeah, are there architectures out there that will take advantage of state space and attention, or is there always this trade-off? Yeah, I think there should be a way to combine them. I think we have been trying to combine them. Like you can do, I mean, these ideas have kind of showed up previously as well, which is you do a block, you do attention within one block, and then you do recurrent across blocks. That seems like a sensible idea. I think you can try different combinations. I haven't seen one that sort of outperform all the rest. There's probably something out there, something clever. Right now, I'll talk about it as well. So right now, sort of the simple way to do it is to just combine them. You have some layers that are Mamba layers or state space, and you have a couple of attention layers, and that seems to do really well as well. So practically, short term, I would advocate for using these hybrid models. I think longer term, there's an academic question of do we need attention at all? All right, great questions. Okay, so let's move to the second half of the talk. So as I mentioned, nowadays test time compute is what's really driving a lot of the progress in AI. So nowadays, when we think about model design, we should actually think about inference first. So I call it inference first model design. So what does this look like? So for existing models, then we want to look at how for example, attention is optimized for inference. So during inference, you have a KV cache, which is as long as the history, and you have a new query, right? So you want to compare the query to the rest of the history, and the way to do that is you can parallelize the work. So this is a work we did with Meta, where you can split the KV cache into, in this example, we split into 5 splits, right? And then do a parallel sort of local attention to each of those. And then as long as you store the log sum x or the softmax denominator of each of those splits, you can combine the result to get the correct output. And this is now used everywhere. I think if you run LM inference, you're almost certainly using this algorithm. So that's how people have been optimizing attention for decode, which is when it's very much memory bound. Most of the time is loading memory, so we want to parallelize as much as possible to maximize memory bandwidth. But one emergent, one architecture that's been adopted pretty much everywhere is GQA, group query attention, where you have multiple query heads attending to the same KV head. And the motivation is you want to reduce the size of the KV cache. That's where most of the time is spent. And so how do you optimize for that? Turns out at the hardware level, you really don't like, you're really operating at the granularity of like 64 or 128. That means that like the hardware wants to do matrix multiplication a block 128 by 128, something like that, right? But if you have one query, or if you only have a couple of query vectors, it really doesn't sort of fill up the tensor core. And so you end up wasting a lot of the compute. So for example, you might have 4 or 8 query heads attending to the same KV head. So you might stack them. So you might stack, let's say, if you only have one query multiplying by the KV, and you're essentially wasting the tensor core. The tensor core can do like 64 by 128 or 128 by 128 matrix multiplication. But essentially, you're only doing 1 by 128 multiplication. You're wasting most of the flops, like 95% of the flops, right? So it turns out you can pack things differently. You can pack multiple query heads into the same sort of matrix multiplication, and that allows you to get much better utilization of the hardware. And this theme is going to come up again and again, where we want to use the hardware efficiently. We want to think about the arithmetic intensity, and I'll talk about that in details. So here's an example whether you do packing different query heads in GQA into one sort of matrix multiplication block or not. In flash attention 2, we didn't do it. We did it for some very special case only. But in flash attention 3, we did that. And in a lot of cases, you see a difference of on the order of 4x to 8x better inference throughput just for the kernel, right? So these things really do matter. So now, how do these different attention variants map to the hardware efficiency? So I would argue pretty much it's all about the arithmetic intensity, which is how many flops do you perform per byte that you load, right? Because at the hardware level, this is called a roofline analysis. So on the x-axis, this is arithmetic intensity, which is how many flops you do per the bytes you load, and on the y-axis is the attainable sort of computational performance, and it's measured by teraflops per second, right? So this is on an H100. So at the top, there's this computational roof, which says that the device, the theoretically maximum amount of compute it can do is around 1,000 teraflops per second, right? But there's also this roof called the I/O bandwidth roof, which is that if you're loading too many things, then you won't be able to do that much flops, right? Because the device has some peak bandwidth, right? The peak bandwidth is, in this case, around 3 terabytes per second, right? So if you're loading 3 terabytes and you're only doing one operation per the byte you load, then the maximum is going to be around 3 teraflops per second, right? So that's the case if you do multi-head attention, right? Essentially, every time you load the KV, you're only multiplying with one query. So you're doing 1, maybe 2, depending on how you count, 1 or 2 flops per the bytes you load, right? And so you get really low sort of attainable computational performance. But as you start sharing some of these, you have more query heads attending to KV heads. You start to get better and better, higher and higher computational performance. So for example, if you use something like GQA or MQA, which means you have more query heads attending to the same KV head, then you get higher computational performance. And with DeepSeek, one of the things that I think they didn't talk about in the paper, but it's only in the config, is that they use a very large number of query heads, right? They use 128 query heads attending to the same sort of latent K and V. So the arithmetic intensity is actually really, really high. It's close to 300, which is sort of this sweet spot of where you're maximally using the memory subsystem as well as the compute subsystem. And I would say this is sort of the right direction, thinking about inference, hardware efficient inference. Yeah.
Might need to refresh my memory a little here for how these group detention mechanisms work. But like in these systems, they're training with the modified attention.
as well, right?
Yeah, the training with the modifier.
And now you're looking at like efficiencies based on like test time efficiencies. And how do we know, like, do you have a reasonable sense of the performance trade-off? So this is like computational efficiency, let's say perplexity or with regards to like, you know, the context dependence and movement, this type of problems. We have a sense of you know, the trade-offs here.
Right. Yeah. So what's the trade-off in terms of quality? So generally, so you can talk about trade-off in two ways. One is you hold the number of parameters constant, and you look at the quality. The other is you hold the flops constant, and you look at quality. So the two are different because when you do something like GQA, that means you share a bunch of query heads attending to the same KV. You actually, you know, that means you reduce the number of parameters in the KV projection. So if you want to hold parameter constant, then you want to increase parameters elsewhere. And if you do that, then generally GQA would perform a little bit better than MHA. Now, if you hold the flops constant, then that means GQA is going to have fewer parameters than MHA because, you know, some of the things are shared already. And then GQA would be a little bit worse. And the other variants are similar. So as you go up the arithmetic intensity, if you hold the parameters constant, because just more parameter sharing means you do more flops, then if you hold parameter constant, they do better in terms of slightly better in terms of quality. If you hold flops constant, then they do slightly worse in terms of quality.
Yeah, I mean, in a sense, what we ultimately want is like, you know, both the delta's constant. But like a proxy would be something closer like with serial runtime because it's like when it's not clear the flops are dominating the cost here, right? Because,
So during training, the flops is dominating.
right.
So these variants would train slower. Yeah. These.
Oh, I see. But we're doing it for inference.
Yeah. So during inference, you're sort of load. If you say, oh, I'm going to load the same amount of KV cache, but then I get to do more computation during inference, yes, the quality will be better during inference. Great question. Okay, so how do they actually work in practice? In some sense, this is the roofline analysis is a theoretical device. You know, just looking at what is the maximum thing you can do. These dots actually measure empirically. So there exists implementation that sort of hit pretty close to the limit. So here's an example where we're measuring DeepSeek flash MLA. Across different sequence length with relatively large batch and large number of query heads. Also, you know, Flash Attention 3 has an implementation for MLA, and this is doing decoding. So you're decoding one token, and on the axis, on the y-axis on the left, we're seeing that it can get close to like 600 teraflops per second. You know, 60% of the theoretical max flop, which is actually amazing. You know, if you just do matrix multiplication, you get to like 70%, 80%, right? So that would consider flop bound or compute bound. And this is during inference, you're decoding one token, and you're already hitting, you know, 600 teraflops per second. So that's amazing. And on the y-axis on the right, this is you're hitting 2,700 gigabytes per second. And remember, the max is like 3.3 terabytes per second. So it's like 85% of the memory bandwidth. So this is hitting 60% of the compute and 85% of the memory bandwidth. So this is what I mean by it was designed very much to like very efficiently use the hardware during inference. And this is one of the, I think, one of the first architecture to hit compute bound during decode. Because I think all the other architectures are pretty much memory bound during decode. So more recently, my student Ted, he's been working on some improvements on this. So it turns out MLA is great, but it's really a pain to shard during inference because you only have one latent KV. So it turns out, you know, the simple idea is you can actually just shard that into two. You turn that into two groups. So on the left, if you have MLA, all of these queries will attend to sort of the same latent. On the right, we're showing GLA group latent attention, where half of the query heads are tending to one latent, the other half are tending to another latent, which is a way to start. And it turns out it works in terms of quality just about as well, but it's a lot easier to shard. And in some cases, it can be up to 2 times faster. So if you're doing something like speculative decoding, where you're not just decoding one token, you might be verifying 2 tokens or something like that, then GLA can be about 2x faster, simply because MLA is already sort of compute bound if you decode 1 token. So if you want to decode 2 tokens or more, you probably want to use some variants like GLA that can that have better efficiency for decoding 2 tokens at a time. So coming back to sort of, so we've seen that attention being heavily optimized for inference as well, and Mamba and RNNs are also very attractive for inference because they don't have this large KV cache. But there's different trade-offs in terms of quality, as we've mentioned. So I think the most straightforward way of people have been adopting these architectures is they do a hybrid, where they take most of the layers being Mamba layers or MLP, and having a couple of attention layers. And you can have around 10% of attention layers and do really, really well. Turns out that's kind of the optimal ratio. And lots of folks have been adopting this kind of hybrid architecture, from Microsoft to Nvidia, Mistral, IBM, and so on. And I think for a while, one of the most challenging aspects is the sort of the ecosystem, which is really hard to use these new architecture because they're not supported in something that you know and love, things like Hugging Face, VLM, and so on. For a while, they only ran on Nvidia chips, but now they run reasonably well on AMD chips and AWS chips, the Trainium. I think VLM now has pretty good support for some of these Mamba and hybrid models. So we've been really excited about working with some of these folks. So I'll talk about sort of the why you would want to use these hybrid models. So this is drawing from some collaboration with folks at Nvidia. So the folks at Nvidia, they were excited to try some of these architectures, but obviously you shouldn't trust anything that's written in a paper. Like you should verify, right? So the way they verified was they took their training setup, same data set, same hyperparameters, and so on, and they already trained their transformer. This was 8B transformer trained to 3.5 trillion tokens. So they took that same setup and they trained a Mamba 2, a pure Mamba 2 model. So in a lot of evals, the Mamba 2 model were around the same, but in MMLU, it was a little bit worse. And this sort of makes sense. MMLU, when you evaluate, you need sort of 5-shot. Usually people do 5-shot MMLU. And in-context learning requires the ability to sort of copy some of, sort of attend to the previous content. So the Mamba models were a little bit worse. But when they add in a couple of attention layers, that seems to solve the problem. And the Mamba 2 hybrid actually does a little bit better. So they try to be as a sort of apple-to-apple comparison as possible. So you can see that the hybrid model actually, I think, outperformed both the pure transformer model and the pure Mamba model. So that's really exciting. The folks at AI 21 have been using it as well, and the motivation for them is that they can train a large model and get better inference end-to-end latency for really long context. Because if 90% or 80% of your layers have linear scaling, that's still a lot better than all of them having quadratic scaling in attention. So they're able to get around 2.5x improvement in terms of end-to-end latency for these really long. And more recently, I think the Nvidia folks got excited about it. So they did this 8B comparison, and they were pretty excited about it. So they started training a much larger and trained for much longer model. So I think this came out a couple weeks ago, was announced a couple weeks ago, and I think the model weights were released a couple of days ago. 2 days ago, yeah. So they train an 8B and a sort of a 50B hybrid model trained to 20 trillion tokens. And this is sort of like all of the things I've ever wanted to validate, right? Like there were a lot of questions, like does it work at scale? Can you quantize it? Does it work at long context? And so on, that the Nvidia folks have validated. So the way they do the hybrid is pretty interesting. I think they do some kind of neural architecture search to figure out where to put the attention layer. It turns out around 8% seems to be optimal. I don't know why. So you would have, I think, most of the layers being Mamba and then FFN, Mamba and FFN. But once in a while, you insert layer. I think it's around 8% layers attention. They found that to be optimal. And after they trained the models, I think they found that there were pretty good trade-off in terms of quality and efficiency. So this the x-axis here is the throughput, inference throughput for long context, and the y-axis is MMLU pro accuracy. So higher is better on the y-axis, and on the x-axis you also want higher throughput is better. So they found that with this kind of architecture for long context, you can get faster inference and maintain really high quality. And they did a bunch of work on the ecosystem side as well, which I didn't really expect. So they were doing things like FP8 training, long context, multimodal, and so on. So that's Nvidia. I mean, they trained. I think they were training it for months on 4,000 chips. But for most of us, that, that's not something we want to do. So what if you want to have a hybrid model, but you don't want to train from scratch for 3 months, right? And turns out you can also do distillation from a pre-trained transformer model. So what you can do is you take the transformer weight, you do a little bit of weight transfer. Turns out there's some correspondence between the sort of QKV projection in the attention layer and these ABC and delta in Mamba. So you can do some weight transfer, and then you do distillation. So with about, I think, 10 billion tokens, you get actually a pretty strong model. So I think this is on the x-axis is how many billion tokens that you do, and on the y-axis is average accuracy. So you can take a phi model and you can distill from that, and you get a pretty strong model with, I think, 6 or 8 billion tokens. It's usually, it's a better trade-off than training everything from scratch. So the message is distillation still works quite well with very few tokens. So one of the last things I want to talk about is test time compute, right? And nowadays the way I think about model architecture is just is an engine that takes in flops and data and convert that to capability. So a better architecture is just a more efficient converter of compute and data into capabilities. So we want to design model to use the compute wisely. And nowadays, a lot of compute is shifting towards inference. As you do test time inference, you do large batch sampling and so on. So for these Mamba models, I think generally if you distill, you're going to lose some quality. That's unavoidable, right? But you get pretty significant gains in terms of inference throughput. So here's an example where we compare, I think, just a 3B llama model with a 4B or 3B distill Mamba model, right? And we're measuring inference time. And generally, as you increase the batch size, the attention will take proportionally more time. And so at large batch size, the transformer model can take maybe 4 times longer to generate compared to a Mamba model, right? But after you distill, obviously you lose some quality. But my point is, you can make up for that by having a much more efficient inference So if you scale in terms of TAM, and on the y-axis, this is coverage, which is a way to measure, if you do large batch sampling, what fraction of the right answer do you generate, do you contain? Then with very limited TAM, the Mamba model generally perform a little bit better, simply because they can sample much more than the Llama model. And this is like a really sort of a fast distillation setup. I think we only distill for like 10 billion tokens. If you do longer distillation, I think you can do a lot better. But this is just sort of proving out the idea that you can distill to change the architecture and get better test time compute scaling. So here's another example of distilling from DeepSeek R1. So we took DeepSeek R1, 1.5 billion. That's the smaller version already. And then we distilled to Mamba for, I think, 10 billion tokens or something. It's a tiny thing. And then if you plot the accuracy, this is a math data set. If you plot the accuracy by the number of samples, then the original model, DeepSeek R1, is going to do better than the distilled Mamba model. So that's not a surprise. But if you plot by normalized by TAM, then we see that the distilled model actually does very reasonably, like very competitive with the original model. And this is with, I think, 10 billion tokens of distillation. So this is very encouraging. So if you don't want to pre-train a large models, I think distillation could offer a pretty good trade-off in terms of quality and inference throughput. And inference throughput nowadays can be converted into model quality. Right. So I'll conclude with a couple of open questions. Here are the things that I don't know or I'm trying to figure out. One is on the modeling side, why do hybrid models do so well? This I don't quite understand yet. I think the attention is doing some kind of retrieval. We need a couple of layers that do that, but precisely how they do that, I'm still trying to figure out. And then on the ecosystems and algorithm side, I think there's still a lot to be done, right? A lot of systems have been written sort of tailored to transform architecture. Things like distributed training with tensor parallel, context parallel, and so on. There's a bunch of open questions there, how you would do it with a non-transformer architecture. And if given test time compute is so important, what is sort of the right, what is the ideal architecture for test time compute? How do we design an architecture that's inference first? I don't think right now any of the things I've shown you is sort of exactly the right answer. But we're taking steps towards that. Things like state space and RNNs could play some role because of large batch sampling. Attention seems still quite important. So I think in the next 6 or 9 months, hopefully we'll figure out what's sort of the ideal architecture for inference TAM scaling. And coming back to the hardware, still a bunch of things to optimize as the hardware evolve, right? Like new background GPUs have a bunch of new features that I'm excited about that we're gonna go optimize for. If you're gonna deploy these things on phones, how do you optimize for that kind of setting as well? So those are sort of new use cases and new hardware that we want to work on, or I personally want to work on. So with that, I will stop here. I'm happy to take more questions. Yes.
Really interesting that, like, as you kind of blow up the hidden space, this gives you kind of something closer to, like, you can store more stuff, right? And then later you were saying that, like, adding a couple of extra, mostly Mamba, but then a few attention layers also kind of helps with you. And are you aware of any work kind of like looking at the trade-off between these things, right? Like, if I kind of shrink that hidden state, do I need more attention layers? Or if I kind of grow it, do I need less?
I see. So there's a trade-off between increasing or decreasing the hidden state and how many layers you need. Yeah, that's an interesting question. I think we've seen, I don't have hard numbers on this, but generally the moment you add a couple of attention layers, the effect of increasing the state size is much less. You still get a little bit of improvement, but it's much less. So one example is when we did Mamba 1, usually we choose state size 16, and then we did Mamba 2, we usually choose state size 128 because it fits the tensor core better. But some folks have found that for hybrid architecture, you only need state size like 16, and that works well enough. So maybe the intuition here is like you don't need to put as much information in the states if you have a mechanism to sort of retrieve information. It's a great question. Yeah.
It's like for attention, people have been doing like
Yeah, so on attention, people have been doing approximation. Is there an analog? Have people been doing similar things for Mamba? I would say I don't think Mamba is sort of exactly the right thing that people would then approximate. Like there are multiple variants that you can do that all do pretty well. Some of them do actually slightly better than Mamba at the cost of being a little bit slower. But I don't think they make a big difference. One thing people have done is sort of start to see if like quantization makes a difference. People started doing pruning some of the heads. I think the Nvidia team have started doing that, but it's very much early stage. My intuition is that for Mamba and RNNs, you already do a lot of compression, so maybe you don't need a lot of these other techniques. But for attention, things like people do tons of compression on the KV cache. Actually, like there's papers saying you can use 2 bits for KV cache even, right? Or you can tie KV cache across different layers, and that still work well, right? So it's quite clear that you don't need that many attention layers, or you might not need to attend to all of the history, right? So I would view it as pragmatically, you can take attention and you can approximate or quantize and sparsify that, or you can sort of put it in the architecture and say like model, I give you the freedom to compress. You get to choose what to put in your memory. Yeah.
I think in general, what is the property of the sequence data that makes Mamba really good? For example, like if I want to use other sequence data that's text,
right?
What should I be?
Yeah. So what kind of domains or data would Mamba do well on? I think is a pretty strong general purpose sequence model. So we've seen good success with audio. So Albert also at this company, Cartesia, they've been using some of this stuff for text-to-speech model, and the models are quite good. Cartesia. I think video would be good as well. Basically, our intuition is that these all started out as sort of continuous time sequence model, right? And with common filter and so on. So anything that sort of move more continuously, like audio and video, I think these things will do well. Text was sort of one of the last domains that was really hard to crack, and it took us a while. I think we needed this sort of selective state space, that the ability to adjust the ABC depending on your input. That was the core idea that made it work for text. But I think the other domains, audio, video, probably genomics as well, you do quite well.
So I have a question about, you talked about the memory, like HBM memory and HBM memory in the beginning of your talk. I'm very interested in, or what if I wanted to implement this myself? I'm not used to like controlling the memory. Is there something between PyTorch and CUDA I can use?
Right.
Besides, of course, the flash attention module?
Right. So if you want to do fine-grained control of this stuff, what should you be using? I would recommend Triton. So Triton is this sort of domain-specific language embedded in Python from Philippe Poulet, and now he's at OpenAI. I think it sort of looks like Python, but you get to control, when to load memory and what computation to do on device and so on. Actually, I've been forcing all of my students to go through the Triton tutorials, and apparently they're having a good time. At least that's what they told me. So I would recommend doing that. Just look up Triton tutorial. It might take you maybe a couple of days to get comfortable with that, and that would give you, I think, 80% of the control at 20% of the pain.
Yeah.
Right. And if you really, really need the last 20% of the control, then yeah, you go down to the lower level, which is much more painful. I would not recommend as a first step. Yeah.
There's like whether you talked about like distributed training, whether there are these like people have investigated like hierarchical SGD, like local SGD type scenarios, whether you think there are sort of unique opportunities in the Mamba-like architectures compared to other architectures, and maybe in a similar point, like how's the fault tolerance in Mamba in the sense of like in transformers, if one of my blocks just like break, I can skip, and then generally it's okay. How about Mamba?
Right. Yeah, distributed training, local SGD, and so on. How does it work with Mamba? The short answer is I don't know. We haven't really tried it. My intuition is that there's some sort of new opportunities that will open up. So these linear time layers are sort of the way you perform the forward pass and backward pass is very much you perform by chunk. So you like compute for one chunk, you pass information to the next chunk, and then that processes information and passes to the next chunk. So it has this really flavor that you're doing some local computation, and then you pass information to the next chunk. And so you might be able to skip some of this. If you care about fault tolerance, you might say, oh, I'm supposed to get the information from my previous chunk, but that one is missing, or the GPU is missing. Maybe I can get information from the one before that. So I think there's probably something to do, especially as you go super long context where you need context parallel, essentially parallelism across the sequence length. So you need to pass information along the sequence length. But a lot of this is not yet explored.
A quick question with regards to your insights for like how much we know about like actual long context models, because it seems like there's a point at which like the Red models, like my gut feeling is like they work pretty well up to like a certain context, and after that I'm not convinced we really understand, we have the right benchmarks to test how well it's working, the data, there's not that many like truly long context models. So do you have a sense of, how do you think about, say, benchmarks for long context? And it is plausible to me that maybe in very long context, the architecture should be a bit different, because maybe we shouldn't remember like all the little details.
Right.
Yeah, so sort of a lot of questions.
Yeah, absolutely. On long context, yeah, I agree with you. I don't think we have the right benchmark. So needle in the haystack is sort of the most popular one, and it's kind of is kind of easy, and all of the model passed that test. And then people started doing like multi-hop reasoning along long context. That's probably more interesting. There's this work from Beatty Chen's group at CMU. He has this benchmark called GSM Infinite, where essentially they construct sort of longer and longer math questions that you sort of need multi-hop reasoning. And we see that the model there's a sense in which after a certain context, the models just don't do well at all. I think OpenAI, with the recent release of 4.1, they also released I think 1 or 2 benchmarks along this direction, multi-hop reasoning. So that's probably where we're heading. I agree. Right now we claim to have long context models, but probably they're not doing that much long context. It's more like they don't blow up, or they can detect needle, but they don't do much. They don't seem to do that much beyond that. Yeah.
So what's kind of beyond to do software hardware design? Do we think the Blackwell architecture will bring about, or what are the most exciting aspects using hardware?
Right. So software, hardware co-design with Blackwell. So something I'm pretty excited about is the larger NVLink domain. So in Blackwell, you can link 72 GPUs together in fast NVLink, and I think that's going to allow super long context for things like video training, where previously the way people were doing it is they would have tensor parallel across 8 GPUs. So you split like the attention heads across 8 GPUs. Those will have fast interconnect with NVLink. But when you do context parallel, you need to start communicating over the InfiniBand, and that gets a lot slower and much higher latency. But now, if you have 72 GPUs connected together, you can do both tensor parallel and context parallel within that NVLink domain. And I think that's going to probably one of the things that's going to unlock really good video model. That's one application that I'm excited about. I think in a year, video models will be really good, and we will have real-time video generation. So that's going to be necessary for training. I think inference is the same. Video generation, inference is actually very flop heavy. And we've worked on some of this at Together AI, and parallelizing across 8 GPUs starts, it's okay, but once you start going beyond 8 GPUs, it's like a lot slower. But what if you can parallelize across 72 GPUs and have real-time, very high-quality video generation? I think that's going to change a lot of the workflow. And some of the companies are starting doing this, pitching to Hollywood and so on. There's probably a market there. Yeah.
You mentioned a lot about optimizing farm. Sounds like SSMs are very matter about. When most of the hardware is out there, are you aware of any works that try to optimize SSMs for modern hardware, or is SSMs fast enough that you don't need to have to?
Right. So is our SSM, how well are they suited for modern hardware, given that the chips are very flop heavy, right? So at the end of the day, it comes down to this arithmetic intensity, which is how many flops you do, how many bytes you need to load. And the ratio is around 300. It's going to maybe increase to like 400, 500, and something like that. I think in state space and RNNs, there's usually a knob, which is the state size, that lets you control how many flops you're going to do per bytes you load. I think right now, because the implementations are not super optimized, so we're not hitting close to hardware limit. But I think we probably still want larger state size, maybe adaptively growing the state as the sequence length gets longer. That makes sense intuitively. Turns out it's actually quite hard to do in practice. So we have an ongoing project trying to do that, but it gets very hairy very quickly. So there's probably some knob you want to tune that that lets you do more compute per memory. But I think the arithmetic intensity is not going to increase that fast. It's going to stay at like 300, 500 or so. It's not going to go 10x. It's going to increase a little bit every generation, because the tensor cores are getting faster, but the memory is also getting faster. HBM3, HBM3E, now HBM4, and so on. So that ratio is increasing, but not that dramatic.
Thanks, Trey, again, for a great talk.